Welcome, listeners, again to our next topic of discussion in the series of lectures on fundamentals of geology. So, the next topic is topic that is very important, obviously stratigraphy, to interpret the geological past of our Earth. So, there are a few principles that I feel is important at the fundamental level as well, that needs to be understood at your end, so that you can obviously deal with different kinds of rocks from different places as well, not only in a specific location. You can relate between rocks that are occurring at different locations on the surface of the earth, and you can correlate between them. So now, if I start with our discussion on stratigraphy, obviously it means, the term means the study of stratas, that are beds that we can see, that we can appreciate in our hand specimen, or be it some outcrop. We can appreciate that bed or structure that is related to it. So obviously it means the analysis or the study of the stratas. So, stratigraphy study of temporal relationship in sedimentary rock bodies. Sometimes they are obviously associated with igneous rocks and metamorphic rocks as well. It reflects changes in balance between rates at which space is produced and filled. Can be considered the history of past geological events, like I was saying, that it will help you to analyze and assess and also correlate between different geological events that has shaped our mother earth. The stratigraphic record preserves details like processes of mountain building. We were talking about in our previous lecture about orogenic cycles and orogenic styles. Then obviously processes of transgression and regression, means your transgression of your marine transgression, means progression of your seawater towards your onshore, and obviously regression of seawater towards offshore. And you also have some climatic fluctuation can be interpreted based on your stratigraphic information. There are a few principles of stratigraphy. The first one will be discussing one by one, but you can see from this example that a rock sequence like this, from for example age of Precambrian through Cambrian, Devonian, Mississippian, Pennsylvanian and till Permian, how these rocks are associated with one another through some events of unconformity in between, some events of erosion, some events of non-deposition and other events, how a whole sequence is related to one another. And if I want to drill past our earth history, then obviously I need to know that which rock type or which lithology or which bed or strata is related to a particular age. When it was formed, we need to have an idea about that. So based on this purpose, that how to interpret the past geological records, the first principle, there are a few principles, starting with the law of superposition, law of original horizontality, law of lateral continuity, based on cross-cutting relationships between the rocks, presence of inclusion, law of faunal succession. Sometimes some incomplete record might also give you some idea about some geological events. Then base level changes, accommodation space, preservation potential, cyclicity, Walther's law, and different ways of correlation of your lithologic correlation that we will be also taking up in these two lectures on stratigraphy. So, the main objective again is to establish a systematic framework for understanding the relative ages of rock layers and reconstructing the Earth's geological history. So, it provides a set of rules and guidelines for interpreting the sequence, relationship and characteristics of sedimentary rocks that we were looking into. By applying these principles, obviously geologists can determine the order of deposition of rock layers, identify geological events such as folding, faulting, erosion, and also draw a correlation between different rock sequences across different location. Like I was referring to, it is not necessarily that you have to interpret some geological events based on a localized or a local signature. You can take multiple signature across a region, and then you can correlate and interpret a larger means interpretation will be of you can say larger implication. So these are the 13 main principles. So we'll be looking into them one by one, starting with the principle of superposition. So in an undisturbed sequence of sedimentary rock, when your sediments are getting deposited one by one, getting into the process of diagenesis followed by lithification, so it will obviously the rock layers, I can simply say, if it is not a disturbed area and it was the basin somewhere, and the rock sediments got deposited one by one, later on that got modified into a sedimentary rock through the process of diagenesis and lithification, then I can simply say, just by looking at a section of that basin, I can say the rocks which are present at the bottom part of the basin are definitely older. The rocks which are present on the upper part of the basin or on the top part of the basin are definitely younger. So it was proposed by the famous geologist who was not actually a geologist. Later on he turned into a geologist, Nicholas Steno. So each layer, he proposed that each layer is younger than the one beneath it and older than the one above it. So this principle serves as a fundamental concept in determining relative ages of rock layers, and it helps to establish chronological order of deposition within sedimentary sequences. So you can see this diagram where your older rocks are sitting at the bottom, your younger rocks are sitting at the top. And if you can remember about the primary structure, sometimes these layers are associated with different primary structures. For example, a crossbed, we discussed about trough crossbed, that if there is a trough crossbed, you can simply, by looking at the geometry of the crossbed, you can have an idea that whether you are looking into a normal sequence or an inverted sequence. You can simply derive that information from the presence of this strata as well as the sedimentary structures associated with these stratas. Then you also have the principle of original horizontality. It is also quite simple, that as the sedimentary rocks are initially deposited in horizontal or nearly horizontal manner, so they will try to be, or they will try to continue laterally in the horizontal manner only. So this principle states that the layers of sediments are laid down parallel to the earth's surface. Means any deviation from this horizontal deposition indicates that there has been some kind of disturbance, some kind of deformation that has tilted the rock layers, like that of folding. So if I fold a rock, there are obviously some changes in this law of original horizontality. It will no longer remain horizontal, it will be folded, and from that also we can, after that we will be using terms like we did in ductile structures, like antiformal anticline, antiformal syncline, synformal anticline, synformal syncline. So those terms will be based on an idea of both the geometry of the structure, where the closure is towards the up or towards the bottom, as well as based on the stratigraphic top and bottom. Based on that, it can be also grouped as anticline or syncline, and a combination of the geometry and the stratigraphic top and bottom, these four types of subcategories of your this antiformal anticline to synformal syncline can be identified. Then you also have the principle of lateral continuity, that sedimentary layers extend horizontally in all direction until they encounter a barrier. That means a kind of a basin or kind of a depressed zone, if is there, it will try to continue laterally unless it is embarked or delimited by some kind of, or limited by some kind of wall or margins. They may thin out, grade into different types of sediment, or terminate against the edge of a depositional basin. This principle helps to correlate rock layers across vast distances and infer the original extent of sedimentary deposit. It implies that layers observed at surface may extend beneath the earth's surface, allowing for extrapolation of geological features. So even if you can't see a sedimentary rock layer, means you are looking at a basin, you are getting some sedimentary rock layer, you can simply think, even if you go outside the basin, you can think that at level that sedimentary rock is going beneath you. So if there is a kind of a basin like it. So here you are standing and you are observing a sedimentary rock layer like this, then even if you go at the top, you will still say that this sedimentary rock is going beneath me like this. What you encountered on the surface in the basinal part, you will now say that sedimentary rock is beneath the subsurface, beneath me. So but this thing will get hampered in case there is presence of some kind of discontinuity, and discontinuity can be of broadly three types: presence of some igneous intrusive contact like dikes or sills. They are also we discussed in the mode of occurrence of your igneous rock. If you can remember, the presence of sills, dikes, sometimes some large scale batholithic intrusion, they can disturb by that. Apart from that, which are the main culprits in, you can say, dismissing this idea or disturbing this idea of lateral continuity of sedimentary rock layers, are the presence of faults and your unconformity. So faults we have discussed in detail, but we have to look into unconformity in a little detail in this discussion. So just if I look at this diagram again, that these rock layers are continuously going from one end to another, they are extended laterally, and if there is an extension like that we get to see in case of horizontal graven structure, or if there is a kind of rifting, then what will happen, that the rocks that are present within this zone of rifting will get detached from its rest of the continuity. So your continuity that was like this earlier will now be like this here, again like this here. So there will be means you can say there will be abrupt termination of beds at each of this fault. Then you can also think of a reverse fault. The first one was a normal fault. You can also think of a reverse fault where your one bed has been transported from here along with the hanging wall to somewhere else like this. So now you have these two continuity, one is going like this, another one is going like this. Again, both are getting abruptly ended at the fault surface. Then you have also lateral shifts that we can see in case of the strike slip faults. So these are again like I was discussing about the termination of beds by faulting. Like this one is a normal fault where your beds are getting terminated about the fault. Here again you have the strike slip faulting mechanism where again your beds are getting separated or displaced along the fault, and here you also have an example of a reverse one where again your beds are getting because here your hanging wall is moving up in relation to your foot wall. So your beds are again getting ending abruptly onto the surface of this. Here is an example of a thrust fault where your older Paleozoic limestone sediments are getting thrusted above your Mesozoic sandstone. So there is also, you can say, it will also not only it is affecting it geometrically, like we can see in this particular diagram on the left hand side, it is also affecting the age connotation, because if you are looking at a Mesozoic sandstone, then on top of it or on bottom of it there is probability that you might get some other rock, but still of the Mesozoic age. But here, due to the presence of the thrust fault that is transporting a Paleozoic limestone on the top of a Mesozoic sandstone, here there are two things are going on. First, obviously there is a change in the lithology of the rock. The lithology is not going or not continuing laterally, as well as the problem is that there is a age difference, that you are no longer, as we move up, you are no longer getting Mesozoic rock layers, you are means you have started to got the or you get the Paleozoic rocks that have been transported from somewhere else, which has been transported now to your place of observation. So a thrust can result into the formation of this kind of, you can say, disturbances in stratigraphic record, because these are discontinuities. So obviously some there will be some changes both in the rock record, the lithology, as well as the age between the two sides, the foot wall and the hanging wall of a thrust fault. So thrust faults also have a larger throw, like we discussed. So it is, you can say, the main or thrust faults can be held responsible for disrupting the stratigraphic sequence of an area very commonly. Then you can also have bed termination by the presence of unconformity. If there is an unconformity, we will be talking about that. So unconformity are nothing but they are events or planes of large scale erosion or non deposition, when no deposition of any sediments is taking place, or there is a large scale erosion of sediments eroding most of the pile of rocks above that surface of unconformity. So that might result into formation of an unconformity, and as the name suggests, that means it is a kind of discontinuity. That means it will also affect the continuity of the rock. So that's why this is also referred to as one of the discontinuity. Like an igneous intrusive body might affect the continuity of a rock sequence. Presence of faults, be it normal or dominantly thrust faults, they will also affect the continuity of the rock sequence. In case of unconformity, which is also a kind of a discontinuity, it will also affect the rock sequence. So now specifically, before going into the later part of discussion on stratigraphic principles, you need to understand also, because we didn't discuss about unconformity in greater detail earlier. So unconformity is a geological feature where there is a discontinuity in the deposition of sedimentary layers. So it indicates a gap in the geological record. Like I was mentioning, if there is a gap in the geological record, they can be also used as an information when you are trying to establish the geological past. So it represents a period of erosion or non-deposition followed by the deposition of younger rocks on top of older ones, and it can occur due to tectonic activity, sea level changes, or other geological processes that might have interrupted the normal or sequential sedimentary processes. Broadly, there are four kinds of unconformities that exist: the angular unconformity, non-conformity, disconformity, paraconformity. So unconformity, they provide important clues about Earth's history, including periods of upliftment, erosion, and base level changes or relative changes in the sea level as well. And it also helps in the interpretation of geological record and also give you an idea about the past environments. So to start with the first type of unconformity, that is your angular unconformity, your younger sediments are deposited on tilted or folded older rocks. So like this, you can see there is a first deposition event in the past, that is followed by an upliftment and tilting. Now a period of erosion has taken place about this level, for example. So after this, whatever rocks will be deposited on above it will have again the rocks that are settling above this level will be now again horizontal, but as the older rocks have already been tilted, so they will have a distinct angular relationship, means like the older rocks will abut or end at the base of the younger rocks, like this. So your older rocks are tilted, or it could be folded in nature as well, and the younger rocks are strictly horizontal in nature. Sometimes they could be also tilted a bit, but the older rock will have a distinct angular difference between the overlying and the underlying rocks. So it represents a period of erosion and upliftment followed by deposition of new sedimentary rocks. The boundary between the older tilted layers and the younger horizontal layer is considered by an angular discordance. So always there is an angular difference between them. It also signifies geological events such as tectonic activity or changes in sea level, providing insights into the past record. So you can see there is a sequence of this event from this level, your erosion has taken place, then you have this erosional surface followed by which there is another deposition of some other rock bodies. For example, you have some rocks which are metamorphic origin. Now after this plane of erosion or series of erosion, now whatever rocks you are getting here is, for example, limestone. So that is also giving you an idea that limestone is sitting directly above your metamorphic rock. They are genetically not related because it is metamorphic in nature. On the underlying rocks, the overlying rock, that is limestone, that is strictly sedimentary in nature. So there is a genetic difference between them, as well as because the rock layer is limestone now, so it might have formed at or beneath the mean sea level. So there has been also a fluctuation or changes in the mean sea level prior to the formation of the unconformity. When there was metamorphic rock, it got buried somehow, or part of it got buried, and then a event of erosion followed by some marine transgression. The marine water has come into that place. Now it deposited limestone, like we discussed in case of when we discussed about formation of non-clastic rocks. So here is a sequence of how an angular unconformity might form. Then you have the non-conformity. This is relatively easier to identify. Why? Because always you have the underlying layers will be always either igneous or metamorphic in nature. The upper rocks or the overlying layers will be strictly sedimentary in nature. So you can also say there is again a genetic discordance, or the two genetically unrelated rocks are juxtaposed over one another. So your non-conformity describes a boundary where sedimentary rocks overlie older and eroded igneous or metamorphic rocks. But again, remember, these are mostly massive igneous or massive metamorphic rock, not layered metamorphic rock, because if you are having a layered metamorphic rock and you have layered metamorphic rock in the underlying rocks, and you have horizontally layered sedimentary rocks on the top, then you can again categorize that under angular unconformity, because that is giving you an angular discordance. But if it is massive in nature, you can't really predict any angular relationship between the overlying sedimentary rocks and the underlying metamorphic rocks. In that case, it will be considered under non-conformity. It represents a significant gap in the geological record, indicating a period of erosion and upliftment followed by sedimentation. Like again, you can see this diagram that igneous intrusion is there within the rock. Again, the whole part, or you can say at this level, till this level your erosion has taken place, then followed by just above it there is again settling of new sediments, which are now will be settled in an horizontal manner. Again, if I look at the law of your your initial law of superposition of beds in an horizontal manner. So again, it is also characterized by distinct differences in rock types, ages and structures between underlying and overlying formation. Like I was saying, obviously they are genetically unrelated rocks of igneous or metamorphic origin, which is extremely, or which is far more different from that of the overlying sedimentary rocks. Obviously there will be some changes or there will be gap in ages, because you have some period of erosion and non-deposition during the formation of the unconformity, and structures obviously will vary. So it will also provide important clues about your tectonic past. So this is again a beautiful example of your angular unconformity, where you can see this is the angular unconformity. These are the underlying rock layers having an angular discordance with respect to the upper horizontal layers. This is an example again of non-conformity, where you can say some igneous intrusion has taken place followed by erosion, and again formation or the deposition of younger sedimentary rocks. You can also compare it with this particular diagram, particular field photograph, where you can relate that there is some massive igneous rock that is sitting beneath this layer, and the upper ones are horizontal in nature. Then you have disconformity if there is a break in the sedimentary rock sequence characterized by parallel rock layers above and below the erosional surface. It represents a period of erosion or non-deposition resulting in a temporal gap in the rock record, that is also referred to as hiatus, temporal gap in the rock record. That is again I repeated it because hiatus is a common word that is used in case of stratigraphy. then it can be challenging to identify because the rock layers above and below, they appear similar, lacking obvious signs of deformation or tilting. In this case, obviously, though there is a period of your erosion and non-deposition, still if there is no tilting or there is no intrusion in there in a sequence or in a rock sequence, then though there is a difference in their age or there is a period of your non-deposition and erosion, still as the upper rocks are also getting deposited horizontally and the older ones were deposited horizontally, it becomes sometimes difficult. But if the surface itself is little bit undulatory or rough, it will be considered as disconformity. If it becomes more problematic, if the surface is means the unconformity surface is strictly horizontal and it is planar in nature, in that case it will be considered under paraconformity. So, again specifically the difference between disconformity and paraconformity is only about the geometry of the unconformity surface. In case of disconformity, it is undulating and rugged and rough in nature. In case of your paraconformity, it is planar, exactly planar and horizontal in nature. So, you can also relate between these two figures, where there is not much difference in the type of the rocks above and below, but there is difference in the type of your means the geometry of the unconformity layer itself. Apart from that, one thing that I would like to mention here, in case when it is difficult to identify disconformity or paraconformity, what is used is your fossil record. If there is fossils of distinct ages in the upper and the lower part, then even in spite of any identification of the unconformity surface, you can identify the presence of an unconformity in between. For example, if you have some trilobites from your Paleozoic era that got extinct during the Permo-Triassic boundary. When we discussed about geological time, I mentioned about the great Permo-Triassic extinction, when the trilobite, it means among several other species, trilobite also got extinct at that time, is present. Some remnants or some fossils of trilobite is present in the underlying rocks. Just above it, you are getting some, you can say some dinosaurian eggs of your Triassic age. So, or you can say of your Mesozoic age. In that case, you can directly say there has to be a time difference between the two rock layers, because prior to Triassic there were no dinosaur. So, obviously there is a time gap, and after your Permian there is no trilobite. So, based on fossil and records or based on the age of the fossils, you can also draw an idea about the disconformity or paraconformity in many cases. So, and it also reflects that a period of erosion followed by renewed sedimentation might have taken place without any large tectonic activity. Otherwise, some of the part of the rock sequence might not have been or might have been tilted during the tectonic activity. So, these are the four kinds of unconformity that you can think of or you can identify in field. Apart from this, till now no other types have been recorded. And before going into the second part of our discussion with principles of stratigraphy, I will also mention last principle in the first half, then again we will be continuing with the rest of the principle in the second part of our discussion on principles of stratigraphy. The principle of cross-cutting relationships: any feature that cuts across a rock or sedimentary layer is younger than the rock or layer it cuts across. It helps to determine the relative timing of geological events such as faulting, igneous intrusion or erosion. Features like faults, dikes and erosion surfaces provide evidences of later disturbances in geological sequences. By identifying cross-cutting relationships, geologists can infer the sequence of geological events and relative ages of rock formation, and it also aids in deciphering the geological history of an area by understanding the sequence of disturbances and the order in which they occurred. So, just if I look at this one, you can say the lower diagram first. So if there is a body that is cutting across through the rest of the layer, so I can say that this body termed as X is younger than ABC, or the other way around, the ABC is much older than this rock body that is marked as X. In the upper diagram again, if I say there are a few rock bodies A, B, C, D, E, F, then I will say that with respect to A, B is older. Obviously, B is cross cutting through all the beds in sequence A. Then with respect to B, C is younger. Why? Because C is also cutting across your B, because B is abruptly ending below C. Then you can think of this movement of the fault, that is, you can say this one, followed by deposition of these layers above the unconformity. For example, C is your unconformity, so you have deposition on the top of the unconformity, followed by again an intrusion of igneous body like that of E, that is getting faulted across F. So like this, simply by looking at the cross cutting relationship between the different lock layers, you can say that which one is older and which one is younger. So here I will end my discussion on the first part of our discussion on principle of stratigraphy. Next we will move to the other principle in the second part of our discussion. Thank you.